Hello dear students, this is the last part of free radicals, part 3, and here I will tell you about the factors that stabilize free radicals. If you have not seen part 1 and part 2, then link is given in the description box, you may check it out. First of all, I ask you to subscribe the channel as well. This is the table of content in which I am going to discuss 3 basic factors that affect the stability of free radical. Stability of free radical increases in order that methyl is less than primary free radical is less than secondary free radical is less than tertiary free radical. Let's talk a bit about stability first. Before going to the geometry and structure, I have to tell you about the stability. So let's just discuss about the stability, how stability is increasing with the order of methyl is less than primary is less than tertiary. Electron poor species are always stabilized by neighboring atom that can donate electron density to them. This is very important line, and you have to understand that by this example that if you are poor, it helps to have rich neighbors. If you are a very poor person, I don't wish that you be, but consider then you have some neighbors that are rich, then they might give you something, some amount, so that to help you out. So by the same way, the free radical that contains some electron donating group, like this is one electron donating group, there are two electron donating group, there are three electron donating group. So more the electron donating groups attached to the free radicals, so greater will be the stability of that radical, because that radical is stabilized by the electron density that is provided by those electron donating species. Okay, so methyl radical is considered as most less stable because it is not having any kind of electron donating species on it. However, it contain one, and then secondary radicals contain two methyl group, and the last, the tertiary, contain three methyl group which are donating its electron density to the radical and thus stabilizing it. Okay, so this is the reason that why the radical stability increasing in this order, because the electron donating species are increasing. Second is factors delocalization or resonance. Free radicals are stabilized by delocalization factor. Whenever there is a resonance in the structure, that there is any delocalization of electron density, then definitely it is going to stabilize the free radical. Secondly, we have to learn the factor that can lead to the electron deficient site being delocalized. Whenever there is a word delocalized, this is about the spreading out of electron density, and it is always a stabilizing factor for the carbocation and for the free radical as well. Here I am firstly going to explain the free radical. Before free radical, I am going to tell you about the carbocation. That carbocation are stabilized by resonance. So just have a look here. This is a cation which is in resonance with this double bond. This double bond will shift to that part, and as a result the positive side will also shift there. Okay, this will happen. The positives will shift to the other part, positive will shift to the other part, double bond will shift to that part. As a result, resonance is going to stabilize, and this is double-headed arrow which says that sometime it will exist in this form and sometime it will exist this form. This resonance or this delocalization stabilizes the free radical. Okay, this is explained in this orbital form as well. So the positive charge is here, then positive charge is here, the double bond resonate itself. Okay, so this is a stabilizing phenomena that carbocations are stabilized by that way. This was about the carbocation, but I'm going to explain the free radicals. So how this will happen? So same as the phenomenon in the free radical as well. However, you have to know about the geometry of free radicals. The geometry of free radicals is about a shallow pyramid. Like shallow pyramid means there is a pyramid, but which is quite shallow, quite not so much up. However, it is somewhat flattened. Okay, if we draw the electron in the typical alkyl free radical, we see that there are three bonding electron and single unpaired electron, a total of four occupied orbital. So in the four occupied orbital, one is having single unpaired and other three are bonding. So if I just explain, then it may be that sp3 hybridized it is. So let's have a look. Free radicals are stabilized by resonance. I told you that as the carbocation are stabilized by resonance, free radicals are also stabilized by resonance phenomena. Geometry of radical is generally considered as shallow pyramid. Let me zoom it, then you will see that this is a pyramid type of shape, but this is somewhat flattened. Pyramid is usually in that form. However, this is a pyramid kind of, but it is somewhat flattened because of the presence of free radical. This means that the partially filled p orbital can participate in the resonance with adjacent p orbital, leading to the greater stability. Whenever there is a delocalization of electron density with the free radical, it is definitely going to stabilize it. Let's have a look at this picture, or this propene free radical, like it's having three carbon, right? 1 2 3, and it is having free radical at one side, and as I told you, the double bond to the resonance with it. As a result, double bond will be shifted to that part and the radical will be shifted to that corner. This can be explained in this orbital form, that it is a double bond that is shifted to the other side. Look at here, it is shifted to the adjacent carbon. As a result, the free radical is also got shifted. Okay, so that resonance phenomena is always stabilizing the free radical as well as it was doing with the carbocation. Let's have an example. It is saying that this free radical is more stable than this one, because here resonance is not present. However, there resonance is present, which is stabilizing the free radical. In the second example as well, here this free radical do not have any kind of resonance. However, this is having in resonance with this benzene ring, which is stabilizing this free radical. So whenever there is a resonance stabilization, then the free radical will be considered as more stable free radical. I hope the point is clear. If it's not, then you may comment down. When the free radical is adjacent to pi bond, it is significant stabilization to be obtained. If the p orbital are in all in line, they can overlap and or make conjugation with it. Overlapping increase, it means that more electron density shifting, more overlapping, the more molecule energy will be lower. You have to remember that whenever a molecule is having its low energy, then it is more stable. Okay, so whenever there is a thing which is said to be at lower energy, it is said to be stabilized. So when the group will be, when the pi bond will be attached, then as a result the overlapping will increase. When the overlapping will increase, the molecular energy will be lowered, and the shallow pyramid is even more flattened out. Now it is a good approximation that now the sp3 hybridized free radical is no more considered as sp3. However, it may exist in the form of sp2 hybridized because of the resonance, because of the delocalization of electrons. I hope you liked the video. This was about the end of the third factor of the stabilization phenomena. I hope the point is clear. Subscribe to the channel, like the video and share it with your friends. Stay safe, stay healthy. Thank you so much for watching.